Okay, so now that we have the notion of dimension, let's go back and look at the dimension of some vector spaces that we've looked at before. Okay, now first the dimension of Cm, or you could do Rm, for example, the column vectors with m components, but the dimension is m because we have a basis of m vectors. Okay, for the dimension of Pn, the polynomials of degree n or less is n plus 1 because we have a basis in that case, 1x up to x, and the basis in this case was e1 up to em, if you remember what those standard basis vectors were. Okay. Now the dimension of matrices, m by n matrices, is mn. Okay, and we found a basis of matrices in this case. All the matrices that have a 1 in one single entry, how many of them are there? Well, there are m columns and m rows and columns, so we have mn possibilities for placing a single 1. So the dimension of mn is 1. Okay, so take a subspace of M22. Now M22 has dimension 4. Okay, and let's see. So let's see if we can find a basis for this subspace. Here we have M22. Here we have two homogeneous relations. Okay. So let's see if we can find a basis. Okay. So how are we going to do that? Let's look at these entries A, B, C, D characterize the matrices. And these two homogeneous relations can be written in matrix form. This first row corresponds to the first homogeneous relation, and the second row corresponds to the second homogeneous relation. If we row reduce, we'll get conditions on the coefficients A, B, C, D. Okay. So in fact, we have A equals minus 2C minus 2D, and B is equal to C. All right, so if you think about that, that means that my first entry A has to be minus 2C minus 2D, and B has to be C. Now we can break this form up into the part that depends on C and the part that depends on D. We've done similar things like that before with column vectors. So if you extract all of the terms that depend on C, here you have the minus 2C in the corner, and then you have a C in the corner here, and C in the corner here, and then you have a 0. Those are all the terms that depend on C. All terms that depend on D are in the second matrix, so I can extract the constant C from the first and D from the second. So here we have a linear combination of these two matrices. Okay. So in fact, the set of matrices A, B, C, D that satisfy the two homogeneous relations above are spanned by these two matrices. Okay, so we can write Z as the span of these two. So now the question is, are these linearly independent? So let's suppose that they are linearly dependent. Try to make a relation of linear dependence. Okay, so if they are linearly dependent, then we can find a linear combination that gives us the 0, that should be the 0 vector. Okay. And if we combine these into one, we get this. Now, if you look at this matrix here, the only way for this matrix to be the 0 matrix is for A1 to be 0 and A2 to be 0, which means this is a trivial linear combination. So that means that these two vectors have no non-trivial linear dependence relation, so they are independent, so they are a basis. Okay, so let's consider dimension of a subspace of P4 with that's spanned by 1, 2, 3, 4 vectors here. All right, now we already showed that this was a basis, so the dimension is 4. We also know the dimension of P4 is 5, as I mentioned before. Okay, so we'll mark that later. Notice that the dimension of the subspace is smaller than the dimension of the space, so that kind of makes sense. Well, we'll prove that formally later. All right. There was this crazy vector space, and I'm not going to go back into there, but there were two linearly independent vectors that span the crazy vector space, so the dimension must be 2. Here's an example of a vector space with no finite dimension. Suppose we take all possible polynomials in X. There's no way to make a basis of this, and you can actually prove this, because no matter what n is, these form a linearly independent set. So I can make n be 2,000, 2 million, 200 million, 2 to the 200 million to the 200 million. So I can always find an unlimited number of linearly independent vectors in this set. That means it can't possibly have a finite dimension. Okay, so that finishes with that section. And I'm going to go on with the next two sections because they're short. We've talked about column space, null space. And now let's talk about dimension in those contexts. Okay, so the nullity is the dimension of the null space, and the rank is the dimension of the column space. Okay, so we can simply use what we've used before to immediately find dimensions of these spaces. For example, if I take this matrix here and I row reduce, okay, so let's see, so we can see what you can see where the free variables are, and you can see where the pivot variables are. So notice that there are 3 free variables, so that means the dimension of the null space is 3. And there are 4 pivot variables, so the dimension of the rank of the matrix, which is the dimension of the column space, is 4. Okay. So in fact, this is always going to be true, and it follows immediately from what we've shown before. No matter what m by n matrix you have, and you row reduce it to B, let R be the number of pivot columns, then the number of pivot columns is the rank, and the number of non-pivot columns is the dimension of the null space. Okay, so from this also immediately we get that the rank plus the null space, the rank plus the nullity is equal to the number of columns. Look back here. If the rank is R and the nullity is n minus R, if you add them together, you're going to get n, which is the number of columns of the matrix. Okay. All right. Now consider the rank and nullity of a non-singular matrix. Okay. So here we have a non-singular matrix. It reduces here. What's the dimension of the null space? Well, there is no null space. The dimension is 0. The rank is n. So in fact, the rank of a non-singular matrix is equal to the number of columns. Okay. So we have the fact that A is non-singular, and the rank is n, which is the number of columns, and the nullity is 0. So those all go together. All right. So here we've added two more equivalent conditions that are equivalent to A being non-singular. All right, those are the 2 that are added down here. We already know this whole list of equivalent conditions for a non-singular matrix. Now we can also say that if the rank of a matrix is n, then that matrix must be non-singular, and vice versa. Or if the nullity of a matrix is 0, then A is non-singular, or vice versa. So that finishes us out with this section.